Egg-shaped sewer. Ovoid shape. Egg-shaped sewer. Ovoid shape. For example, these. Type of closed sewer. That is 1.5 times of their width. Smaller radius at bottom and larger at top. Mostly constructed with RCC. Small d by capital D. 0.25. Avoid 0.7. Small d by capital B. Circular 0.698. Small d by capital D 0.20. Avoid 0.62. Circular small d by capital B 0.61. Small d by capital D 0.1. Avoid small d by capital B 0.44. Small d by capital B circular 0.4. Small d by capital D 0.05. Avoid small d by capital B 0.29. Circular small b by capital B 0.25. Egg-shaped sewer. Advantages: provide slightly higher velocity for low flows over circular sewer of equal capacity. Advantages of egg-shaped sewer: effective in combined system. Disadvantages of egg-shaped sewer: unstable as small end of egg is down and has to support weight of upper broader section. Difficult to construct. Disadvantages of egg-shaped sewer: expensive as more material is required. High construction cost. Expensive as more material is required. Not cleansing in absence of adequate gradient. Not self-cleansing in absence of adequate gradient. Regular shaped. Ease in construction, more stability. This one is advantage. Rectangular shaped. Hydraulically inefficient. Horseshoe shaped sewer. Used for large sewer with heavy discharges such as trunk and outfall sewers. Suitable when headroom for the construction of sewer is limited. Invert of this section may be flat, parabolic, or circular. Crown is semicircular and can support external load without the aid of backfilling. Parabolic shaped sewer. Upper arch of sewer forms the shape of parabola. Used for carrying comparatively small quantity of sewage. Invert of the section may be elliptical or parabolic. Semi-elliptical shaped sewer. Used for soft soil as it is more stable. Useful only for carrying large amount of sewage. Rotary when sewers have width greater than 2 meter. This is semi-elliptical shaped sewer. For example, this. U-shaped sewer. Used for combined sewer having maximum flow of storm water. Used for long sewers and especially in open cuts. Invert is in the form of semicircular arch. For example, this is in the form of semicircular arch. This is U-shaped sewer. Semicircular shaped sewer. The semicircular shaped sewer. This one. The section gives a wider base at bottom and hence it becomes suitable for constructing large sewers with less available headroom. It is outdated. What is sewer materials? Points to be considered: resistance to corrosion, resistance to abrasion, strength, durability, cost, hydraulic efficiency, imperviousness. Sewer materials: asbestos cement, plastic, vitrified clay or stoneware, brick, steel, plain or reinforced cement, concrete, cast iron. Asbestos cement, manufactured from the mixture of asbestos, fiber, silica and cement. Size 75 to 500 mm in diameter and length up to 4.0 meter. Light in weight, easy to cut and assemble without skilled manpower, quick laying and backfilling. Structurally not very strong. Vitrified clay or stoneware, manufactured from clay and shales of special qualities and grades. Used mainly in house drainage and lateral sewers. Size available 5 to 330 cm internal diameter with 0.9 to 1.2 meter in length. Merits: highly resistant to sulfide corrosion due to high velocity. Inner surface is smooth, hence hydraulically efficient. Note: Note: these are merits of vitrified clay and stoneware. Possess high compressive strength. Vitrified clay and stoneware. Enough resistant to corrosion due to grit and silt. Highly impervious, cheap, and easily available. Demerits of vitrified clay and stoneware: weak in tension, brittle in nature, quite bulky and heavy. Vitrified clay and stoneware. Difficult in laying and transportation. Brick, used for construction of large sized combined sewers. Advantage: can be constructed to any required shape and size. Disadvantages of brick: higher cost, large space requirements, slow work progress. Slow work progress. Advantage: can be constructed to any required shape and size. Disadvantages: higher cost, large space requirements, slow work progress. Steel, used for main outfall and trunk sewers, having large diameters where high external and internal pressure are encountered. Perfectly impervious, light in weight, easily welded. Steel can absorb vibration and shock loads due to its flexibility. Steel made corrosion resistant by heavy galvanization or bituminous coating. Steel cost is high compared to the cast iron pipes. Cast iron, available in diameter from 150 mm to 750 mm and 3 to 3.5 meter length. Stronger to withstand tensile, compressive, and bending stress. Can withstand vibration, high external and internal pressure, easy to join and water tight. Cast iron, brittle in nature and expensive. Cast iron, easily acted upon by acids. Cast iron, difficult to transport and handle. Used under following circumstances: heavy external loads, high internal pressure. Cast iron. Cast iron used under following circumstances: crossing low level areas, under expensive road surface, protection against contamination, temperature variations, vibrations, wet ground conditions. Plastic, used for internal drainage works in house. Size 75 to 315 mm external diameter, smooth internal surface. Offer resistant to corrosion, light in weight, economic in laying, jointing and maintenance. Tough and rigid plastic. Ease in fabrication. Plain or reinforced concrete, usually from 80 mm to 450 mm diameter with thickness varying from 25 to 35 mm, equally strong under internal and external pressure, easily manufactured even at site, economical for medium and large size installation, easily corroded by action of contents of sewage. Such corrosion is known as crown corrosion. Plain or reinforced concrete, precast concrete and cast in situ concrete pipes. H2S plus 2 oxygen gives H2SO4 in the presence of bacteria. Then H2SO4 leads to corrosion. Then moisture. This is one is moisture. This is location of hydrogen sulfide oxidizing bacteria. Then this is hydrogen sulfide. This is oxygen, hydrogen sulfide, oxygen, air, hydrogen sulfide, oxygen. There may be the exchange of hydrogen sulfide and oxygen. This is wastewater. Here sulfate SO4 2 negative under anaerobic conditions give sulfide or H2 negative. H2 negative plus 2H positive gives reversible reaction with H positive plus HS negative, which leads to reversible reaction between H positive and HS negative, which further leads to hydrogen sulfide. This is slime layer. This one is slime layer. Here moisture. Here H2S plus 2 oxygen in the presence of bacteria gives H2SO4. Then H2SO4 leads to corrosion. Location of hydrogen sulfide oxidizing bacteria. Location of hydrogen sulfide oxidizing bacteria. Design this section of combined circular sewer from the data given below. Area to be served is 150 hectares. Population locality is 1 lakh. Maximum permissible velocity 3.2 meter per second. Time of entry is 5 minutes. Time of flow is 20 minutes. Rate of water supply is 270 liter per cubic per day. Runoff coefficient is 0.45. Assume suitable data if necessary. Solution: assuming 80% of the water supplied will be reaching the sewers as sanitary sewage, quantity of sanitary sewage produced, average quantity of sanitary sewage flow (DWF) is equal to average quantity of sanitary sewage flow (DWF) is equal to population of locality into rate of water supply into 0.8 liter per day is equal to 1 lakh into 270 into 0.80 divided by 1000 into 24 into 60 into 60 meter cube per second, which is equal to 0.25 meter cube per second. Maximum or peak quantity of sanitary sewage is equal to peak factor into DWF, assuming P factor is equal to 2. Then 2 into 0.25 meter per cube per second is 0.5 meter cube per second. TC is equal to TE plus TF, where TC is equal to time of concentration, T is equal to time of entry, TF is equal to time of travel or flow. The quantity of storm water will be maximum when storm duration is equal to time of concentration. Thus T is equal to TC is equal to 25 minutes. I is equal to 1020 over T plus 20. Then I is equal to 1020 over 25 plus 20 is equal to 22.67 millimeter per hour. The storm water runoff is given by rational formula as Q is equal to CIA over 360, where C is equal to 0.45, I is equal to 22.67 millimeter per hour, A is equal to 150 hectare. Then Q is equal to CIA over 360 is equal to 4.25 meter cube per second. Therefore, combined discharge Q is equal to 0.5 plus 4.25 is equal to 4.75 meter cube per second. Now A is equal to Q by V is equal to 4.75 divided by 3.2 is equal to 1.48 meter square. All the velocity must lie between 0.75 to 3.2 meter per second. Hence 3.2 meter per second is assumed. Diameter of sewer D, capital D, is equal to under root 4a by pi is equal to approximately equals to 1.374 meter. A dotting commercially available size 1.4 meter. Area is equal to pi d square by 4 is equal to pi into 1.4 square by 4 is equal to 1.54 meter square. V is equal to Q by A is equal to 4.75 divided by 1.54 is equal to 3.08 meter per second less than 3.2 meter per second. Hence okay. Check for cleansing velocity during dry weather flow. Small q by capital Q is equal to 0.25 or 4.75 is equal to 1 by 19 is equal to 0.0526. Small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 pi theta whole raised to power 5 by 3. Then 18.94 over theta whole raised to power 3 by 5 plus 360 sin theta by 2 pi theta minus 1 is equal to 0. Solving theta is equal to 93 degree. Small v by capital V is equal to 1 minus 360 sin theta by 2 pi theta whole raised to power 2 by 3, or small v is equal to 3.08 into 0.529 is equal to 1.629 is equal to 1.629 meter per second. 0.75 meter per second less than 1.629 meter per second less than 3.2 meter per second. Hence okay. Check for self-cleansing velocity during minimum flow. Assume Q minimum is equal to 1 by 2 of DWF. Small q by capital Q is equal to 0.0263. Small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 pi theta whole raised to power 5 by 3. Solving theta is equal to 78.0777 degree. Small v by capital V is equal to 1 minus 360 sin theta by 2 pi theta whole raised to 2 by 3, or V is equal to 3.08 into 0.43 is equal to 1.32 meter per second. 0.75 meter per second less than 1.32 meter per second less than 3.2 meter per second. Hence okay. Calculate the diameter and velocity of circular sewer at a slope of 1 in 150 when it is running just full at a discharge of 1.05 meter cube per second. The value of n in Manning's formula is 0.011. What will be the discharge and velocity when flowing 0.75 depth of pipe for the same slope? Solution: use Manning equation we have Q is equal to 1 by n into A into R raised to 2 by 3 into S raised to 1 by 2, where Q is equal to 1.05 meter cube per second, n is equal to 0.11, S is equal to 1 by 150. Thus, substituting we get 1.05 is equal to 1 by 0.11 into pi by 4 d2 into d by 4 whole raised to 2 by 3 into 1 by 400 whole raised to 1 by 2. Then d is equal to 0.7436 meter. Velocity v is equal to 1 by n into r raised to 2 by 3 into s raised to 1 by 2 is equal to 1 by 0.11 into 0.7436 by 4 whole raised to 2 by 3 into 1 by 150 raised to 1 by 2 is equal to 2.42 meter per second. Water flowing depth of pipe is 0.75 meter. Small d by capital D is equal to 0.75. Center angle theta is given by cos theta by 2 is equal to 1 minus 2d by capital D is equal to 1 minus 2 into 0.75. Theta is equal to 240 degree. Small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 by theta whole ratio of 5 by 3. Discharge capital Q is equal to 1.05 meter cube per second. Therefore, small q is equal to 0.9575 meter cube per second. Now, small v by capital V is equal to 1 minus 360 sin theta by 2 by theta whole ratio of 2 by 3. Velocity is small v is equal to 2.42 meter per second. Velocity capital V is equal to 2.42 meter per second. Therefore, small v is equal to 2.74 meter per second. Calculate the velocity of flow in a sewer or circular section having diameter of 1 meter, laid at gradient of 1 in 600. Use Manish's equation. Take small n is equal to 0.012. Small n is equal to 0.012. 1 by m, gradient is equal to 1 by 600. V is equal to Cosima. Q is equal to Cosima. Solution. For sewer running half full, area is equal to pi d square by 8, perimeter is equal to pi d by 2, r is equal to a by p is equal to d by 4. Hydraulic radius capital R is equal to 0.25 meter. Area is equal to pi d square by 8 is equal to 0.3627 meter square. Using Manish's equation, velocity capital V is equal to 1 by n, r raised to 2 by 3 into s raised to 1 by 2 is equal to 1.35 meter per second. Discharge capital Q is equal to AV is equal to 0.3927 into 1.35 is equal to 0.053 meter cube per second. Design a sewer to serve a population of 1,20,000. The daily per capita water supply allowance being 180 liters, of which 80% find its way into the sewer. The permissible sewer slope is 1 in 1,000. Peak factor is equal to 2 and take Manish n is equal to 0.012. Average flow DWF is equal to 0.80 into 1,20,000 into 180 liters per day is equal to 1,20,000 into 180 into 0.80 or 1,000 into 24 into 60 into 60 meter cube per second is equal to 0.20 meter cube per second. Maximum or peak quantity of sanitary sewage. Maximum or peak quantity of sanitary sewage. Maximum or peak quantity of sanitary sewage is equal to peak factor into DWF is equal to 2 into 0.20 is 0.40 meter cube per second. The sewer is designed for maximum discharge. Thus, using Manish's equation, we have Q is equal to A by N into R ratio 2 by 3 into S ratio 1 by 2. N is equal to 0.012. S is equal to 1 by 1000. If D is the diameter of the sewer, then A is equal to pi by 4 D square. P is equal to pi D. R is equal to A by P is equal to D by 4. Thus, by substituting, we get 0.40 is equal to 1 by 0.012 into pi by 4 D square into D by 4 whole raised to 2 by 3 into 1 by 1000 whole raised to 1 by 2. Then diameter raised to 8 by 3 is equal to 0.487. Then D is equal to 0.763 meter. Dot commercially available size 0.8 meter. Check for self cleansing velocity and maximum flow. V is equal to 1 by n into R raised to 2 by 3 into S raised to 1 by 2. V is equal to 0.9 meter per second, which is 0.6 meter per second, less than 0.9 meter per second, which is less than 3 meter per second. Check for self cleansing velocity at dry weather. Dry weather flow. Small q by capital Q is equal to 0.2 over 0.4 is equal to 1 by 2 is equal to 0.5. Small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 by theta whole raised to power maybe 1 by 3. Then over 180 by theta whole raised to power 3 by 5. Sorry, it is 5 by 3. Here it is 5 by 3. Then here it is plus 360 sin theta by 2 pi theta whole minus 1 is equal to 0. Solving theta is equal to 180 degree. Small v by capital V is equal to 1 minus 360 sin theta by 2 pi theta whole raised to power 2 by 3, or small v is equal to 0.9 into 1 is equal to 0.9 meter per second, which is 0.6 meter per second less than 0.9 meter per second, which is less than 3 meter per second. Hence, okay. Check for self-cleansing during maximum flow. Assume Q minimum is equal to 1 by 2 of dWf. Small q by capital Q is equal to 0.25. Therefore, small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 pi theta whole raised to power 5 by 3, or 45 by theta into raised to power 3 by 5 plus 360 sin theta by 2 pi theta minus 1 is equal to 0. Then theta is 1 degree. Small v by capital V is equal to 1 by 360 sin theta over 2 by theta whole raised to 2 by 3. Then V is equal to 0.9 into 0.682 is equal to 0.61 meter per second, which is 0.6 meter per second less than 0.61 meter per second, less than 3 meter per second. Hence, okay. Calculate the diameter of sewer to serve an area of 20 square kilometer with population density of 250 person per hectare. The average rate of sewage flow is 350 liter per cubic density. The maximum flow is 50% in the assets of average together with rainfall equivalent of 50 mm in 24 hours, all of which are runoff. Take the V maximum as 3 meter per second. Solution. Total population of area is equal to 250 into 20 into 10 ratio 6 over 10 ratio 4 is equal to 5 lakh. 5 lakh, yes, 5 lakh persons. Average sewage flow is equal to 5 lakh into 350 into 10 ratio minus 3 over 24 into 3600 meter cube per second, which is equal to 2.025 meter cube per second. Peak or maximum flow is equal to 1.5 into 2.025 meter cube per second. Q maximum is equal to 1.5 times average flow is equal to 3.038 meter cube per second. Storm sewage is equal to storm sewage Q is equal to CIA over 360, where C is equal to 1, I is equal to 0.625 millimeter per hour, A is equal to 2000 hectare is equal to 3.472 meter cube per second. Total flow for combined sewer is equal to 3.038 plus 3.472 is equal to 6.51 meter cube per second. Capital A is equal to capital Q by capital B is equal to 6.51 divided by 3 is equal to 2.17 meter square. Diameter of sphere capital D is equal to under root of 4 capital A by pi is equal to 1.662 meter. Calculate the diameter of combined circular sewer with the following data. Rate of water supply is equal to 100 liter per cubic density. Population density is equal to 100% per hectare. Peak factor is equal to 2.7. Area is equal to 3.35 hectares. Rainfall intensity is equal to 50 mm per hour. Slope is equal to 1 in 750. Rugosity coefficient is equal to 0.011. Runoff coefficient is equal to 0.4. The sewer should run 0.6 full during peak flow. Then solution. Assume 80% of supplied water converted as wastewater. Average flow dWf is equal to 0.80 into 3500 into 100 liters per day is equal to 3500 into 100 into 0.80 into 10 ratio minus 3 over 24 into 3600 meter cube per second, which is equal to 0.00324 meter cube per second. Maximum or peak quantity of sanitary sewage is equal to peak factor into dWf is equal to 2.7 into 0.00324 is equal to 0.00875 meter cube per second. Quantity of storm sewage Q is equal to CIA over 360, where C is equal to 0.4, I is equal to 50 mm per hour, A is equal to 335 hectare. Then Q is equal to CIA over 360 is equal to 0.58 double 3 meter cube per second. Therefore, combined discharge small q is equal to 0.592 meter cube per second. Small d by capital D is equal to 0.6. Central angle theta is given by expression cos theta by 2 is equal to 1 minus 2 small d by capital D is equal to 1 minus 2 into 0.6. Then theta is equal to 203.07 degree. Therefore, small q by capital Q is equal to theta by 360 into 1 minus 360 sin theta by 2 pi theta whole raised to 1 by 3 In full flow conditions, capital Q is equal to 0.88116 meter cube per second. Using Manni's formula, capital Q is equal to A by N into R raised to 2 by 3 into S raised to 1 by 2. Small n is equal to 0.011. S is equal to 1 by 750. If D is the diameter of the sewer, then A is equal to pi by 4 D square. P is equal to pi D. R is equal to A by P is equal to D by 4. Then 0.88116 is equal to 1 over 0.011 is equal to pi by 4 D square into D by 4 whole ratio 2 by 3 into 1 by 750 whole ratio 1 by 3. Then D is equal to 1 meter. Then a city has a population of 1 lakh with a per capita water supply of 200 liter per cubic per density. Design sewer running 0.7 times full at maximum discharge. Take small n is equal to 0.013. Slope is equal to 1 in 600 and peak factor is equal to 2.25. Assume 80% of W by S contributes for sewage. Then solution: quantity of water supplied is equal to 1 lakh into 200 into 10 ratio minus 3 over 24 into 3600 is equal to 0.2315 meter cube per second. Average quantity of sanitary sewage DWF is equal to 0.8 into 0.2315 is equal to 0.1852 meter cube per second. Peak discharge is equal to PF into DWF into is equal to 0.4167 meter cube per second. Small d by capital D is equal to 0.75. Central angle theta is given by the expression cos theta by 2 is equal to 1 minus 2 small d by capital D is equal to 1 minus 2 into 0.75. Theta is equal to 27.16 degree. A is equal to pi d square by 4 into theta by 360 minus sin theta by 2 pi, which is equal to 0.5872 d square. Small p is equal to pi d into theta by 360 is equal to 0.19262 d. R is equal to A by P is equal to 0.2962 capital D. Using Manni's formula, capital Q is equal to A by N into R raised to 2 by 3 into H raised to 1 by 2. Then N is equal to 0.013, S is equal to 1 by 600. 0.4167 is equal to 1 by 0.013 into 0.5872 d square into 0.2962 d whole raised to 2 by 3 into 1 by 600 whole raised to 1 by 2. D is equal to 776 meter. Adopt commercially available size 0.8 meter. Check velocity. V is equal to 1 by 0.013 into 0.23696 whole raised to 2 by 3 into 1 by 600 whole raised to 1 by 3 is equal to 1.20 meter per second. 0.6 to 3 meter per second, hence okay. Check self-cleansing velocity for DWF. Small q by capital Q is equal to 1 by 2.25. Therefore, small q by capital Q is equal to theta by 360 into 1 by 360 sin theta by 2 pi theta whole raised to 1 by 3 maybe. Or 160 by theta whole raised to 3 by 5 plus 360 sin theta by 2 pi theta minus 1 is equal to 0. Then solving theta is equal to 172.42 degree. Small v by capital V is equal to 1 minus 360 sin theta by 2 pi theta whole raised to 2 by 3 is 0.97. Then small v is equal to 0.97 into 1.20 is equal to 1.166 meter per second. Similarly, velocity during minimum flow can be obtained as minimum flow is 1/3 of average flow. Capital V minimum is equal to 0.8545 meter per second. As flow drops to minimum, this self-cleansing velocity will be maintained in sewer, hence design is okay. Construction of sewers. Sewers are expensive to construct, and if not built correctly, remedial works can be disruptive, time consuming, costly, and in some circumstances have adverse effects on a company's reputation. In many instances, a lot of mistakes can be avoided by considering the specification and requirements before during construction. This is an on-site guide for contractors and operators constructing sewers with advice notes provided to avoid some of common on-site errors. Trenching and bedding. Trenches must be adequately spotted free from boulders and tree roots must be taken out. Second, muddy ground, water, and soft areas in the trench base must be avoided. Third, materials spoil and equipment must be stored safely and plants should be operated with a safe working distance. Fourth, the trench must be adequately protected from slips, trips, falls, sight, traffic, and have a safe means of access. Trenching and bedding. First, trenches should be adequately dewatered to provide a firm base, but not dug wider than necessary as excessive loading may be placed on the pipe. Second, should ground conditions be unsuitable for pipe laying and manhole construction, an engineer must be consulted to design a solution. Trenching and bedding. First, in addition, care must be taken to prevent site debris, sludge, or slit from entering the sewer network, which could ultimately cause flow restriction blockages, flooding, pollution, and also affect the receiving wastewater treatment works. Course associated with such incidents may be recovered from those responsible. Third, in addition, such an inappropriate discharge of a site groundwater or construction material cause a pollution incident. This may lead to prosecution. Installation of sewage pipes. The installation of sewage pipes consists of the following steps. First, locate the position of the manhole on the ground along the longitudinal section of the sewer line. It is common practice to lay sewer line between two manholes at a time. The center line pegs of the sewers are driven at a distance of every 7.5 meter or 15 meter. Third, the center line of the sewer line should be properly maintained by providing an offset line usually marked at a distance of 2 meter to 3 meter. The offset line helps in locating the sewer center line when excavation is carried out to laying of sewer pipe. Pipe laying and beddings. First, pipe must be evenly bedded along the length of the pipe, usually full bed and surround for semi-rigid and flexible pipe materials. Rigid pipes may require less granular bedding material. Third, sewers located within highways or areas of traffic should have 1.2 meter of cover. In other areas, 0.9 meter of cover is required. Where this is not possible, a full protected concrete bed and surround must be provided, inclusive of flexible joints. Pipe laying and beddings. Pipe should be laid in 3 meter maximum lengths when the joints pushed home into sockets. Furthermore, care must be taken to ensure the pipe jointing seals are free